The Big Bang theory is the prevailing cosmological model that describes the origin and evolution of the universe. It is one of the most significant scientific theories in modern physics and astronomy, offering a comprehensive explanation for the formation of the universe, its current structure, and its ongoing expansion. Theory fundamentally proposes that the universe began as an infinitely small, hot, and dense point, often referred to as a singularity, approximately 13.8 billion years ago. Over time, this singularity expanded in a cataclysmic event, which led to the creation of space, time, and the fundamental building blocks of matter. From this point, the universe began a continuous process of expansion, cooling, and evolving into the vast cosmos we observe today. The conceptual foundation of the Big Bang theory can be traced back to the early 20th century, with contributions from a range of scientists, particularly in the fields of astronomy and physics. The first major stepping stone toward the Big Bang theory was Albert Einstein's theory of general relativity, published in 1915. General relativity describes how gravity functions on a cosmic scale, especially in relation to the curvature of space-time. Initially, Einstein believed that the universe was static, but the equations of general relativity indicated that the universe could either be expanding or contracting. To account for the perceived stability of the universe, Einstein introduced the cosmological constant, later called the Einstein's blunder, to maintain a steady state. However, this notion would soon be challenged. In 1927, Belgian priest and physicist Georges Lemaitre proposed the idea of an expanding universe. Lemaitre's hypothesis of the primeval atom suggested that the universe began from an incredibly dense point, which later exploded in a violent expansion, akin to what we now call the Big Bang. Lemaitre's insights were based on the equations of general relativity, and his work laid the groundwork for the Big Bang theory. His ideas, however, remained speculative until observational evidence came along in the 1930s. The observational breakthrough came from Edwin Hubble in the late 1920s and early 1930s. Hubble, using the newly constructed Mount Wilson Observatory, discovered that galaxies were moving away from the Earth, with their velocities directly proportional to their distances. This was a clear indication that the universe was expanding. The phenomenon, known as Hubble's law, provided crucial evidence for the idea that the universe was not static but in a state of dynamic expansion. If galaxies were receding from each other, then they must have been much closer in the past, suggesting that the universe had a beginning, and it has been expanding ever since. The Big Bang theory itself encompasses several stages of cosmic evolution, from the initial singularity to the present-day universe. At the moment of the Big Bang, the universe began as a singularity, a point of infinite density and temperature. At this moment, space-time, matter, and energy were all compressed into a single point. The laws of physics, as we know them, break down at this singularity, and our current understanding of physics cannot explain the conditions at this point. This singularity is not thought of as a traditional explosion in space, but rather as an expansion of space itself. Around 10:36 seconds after the Big Bang, the universe underwent a period of rapid expansion known as cosmic inflation. During inflation, the universe expanded exponentially, increasing by a factor of at least 10^26 times in less than a fraction of a second. This rapid expansion solves several critical problems in cosmology, including the flatness problem, why the universe appears to be geometrically flat, and the horizon problem, why distant regions of the universe have the same temperature and properties. Inflationary theory, first proposed by Alan Guth in 1980, suggests that this rapid expansion was driven by a field known as the inflaton field, although the exact mechanism remains an active area of research. After the first few microseconds, the universe cooled sufficiently for subatomic particles, such as quarks, leptons, and photons, to form. Initially, quarks and gluons, the force carriers of the strong nuclear force, existed in a hot, dense plasma. As the universe continued to expand and cool, quarks began to combine to form protons and neutrons, while electrons began to form stable orbits around nuclei, forming the basic building blocks of atoms. This era is referred to as the quark epoch. Approximately 3 minutes after the Big Bang, temperatures dropped enough for nuclear fusion to take place, resulting in the formation of the first atomic nuclei. This period, known as Big Bang nucleosynthesis, led to the creation of light elements like hydrogen, helium, and trace amounts of lithium and beryllium. The universe at this time was still too hot for atoms to form, and it was primarily a plasma of atomic nuclei and electrons. However, this period set the stage for the formation of atoms in the subsequent epoch. Around 370,000 years after the Big Bang, the universe had cooled sufficiently for electrons to combine with protons and form neutral hydrogen atoms. This process, called recombination, allowed photons to travel freely through space, marking the end of the opaque plasma era. The release of these photons is known as the cosmic microwave background, CMB radiation. The CMB is considered one of the most important pieces of evidence for the Big Bang theory. It is a faint glow that permeates the entire universe, a remnant of the heat left over from the Big Bang. The study of the CMB provides critical insights into the early universe's conditions and supports the idea of an expanding universe. Approximately 400 million years after the Big Bang, the universe had cooled enough for gravity to pull together clouds of hydrogen and helium gas. These clouds eventually formed the first stars and galaxies, marking the beginning of the cosmic dark ages. The formation of these first stars, known as the population III stars, played a crucial role in reionizing the universe, ending the dark ages, and paving the way for the formation of more complex structures. As time progressed, gravitational interactions between galaxies, stars, and other matter led to the formation of more complex structures. The universe continued to expand, but galaxies began to cluster together, forming galaxy groups and superclusters. Stars within these galaxies formed through nuclear fusion, creating elements heavier than hydrogen and helium, which would later be incorporated into the formation of planets, moons, and other celestial bodies. The Big Bang theory is supported by several key pieces of observational evidence. As previously mentioned, Edwin Hubble's discovery that galaxies are receding from us with velocities proportional to their distance is one of the most significant pieces of evidence for the expanding universe. The redshift of light from distant galaxies indicates that the universe is still expanding, a prediction that aligns perfectly with the Big Bang theory. The cosmic microwave background, CMB, is perhaps the most compelling evidence for the Big Bang. The faint microwave radiation detected by Arno Penzias and Robert Wilson in 1965 corresponds to the afterglow of the Big Bang itself. This radiation is uniform across the sky, with slight fluctuations that provide insight into the universe's early conditions. The predicted abundances of light elements such as hydrogen, helium, and lithium produced during Big Bang nucleosynthesis closely match observations. The theory successfully explains why these elements are found in the observed proportions in the universe today. The future of the universe is still uncertain and depends on the fundamental properties of space, matter, and energy. Current observations suggest that the universe's expansion is not slowing down but accelerating, likely due to a mysterious force known as dark energy. This acceleration hints at a future where the universe continues to expand indefinitely. In one scenario, the universe could continue to expand forever, growing colder and more diffuse over time. Another possibility, known as the Big Crunch, suggests that the universe might eventually stop expanding and collapse back in on itself. While the ultimate fate of the universe is still under investigation, the Big Bang theory remains the cornerstone of our understanding of the universe's past and its ongoing evolution.